All right, we finished our first Juniper course, which was the Introduction to the Junos operating system. And now we're going to look at routing fundamentals. So what we're going to cover now should be at least a little bit familiar to those of you who have just done the CCNA course. So, so far, we're not going to be putting too much stress on you, I hope. It should be kind of familiar. We are going to go and take a look at some basic routing operations and concepts, which will be a little bit of revision. We're going to look at routing and forwarding tables. So this is a little bit different. When we did our Cisco course, we only looked at routing tables. So we're going to look at the concept of routing and forwarding tables together, because as we saw earlier on, our Juniper device has got a forwarding table, which is a kind of a separate thing to the routing table, but which is populated from the routing table. So we'll look at that. And we're going to take a look at static routing, which should be fairly familiar to you. And we're going to have a look at OSPF, which again should be kind of familiar. So let's just first of all start off by taking a look at routing concepts, and we'll take a look at an overview of routing. So what is routing? Okay, so we're going to go right back to the beginning here, guys. What is routing? The process of moving data between layer 3 networks. So remember when we talked about the job of a router is to get traffic from one network to another network. So here we have an example of a number of different networks here. So the job of the router, or the routers in this case, is to get the traffic between those different networks. So what do we need? For a device to communicate with another device in a remote network, we need two things. We need an actual end-to-end communications path. So we need the physical path to be there. We need to have a cable of some kind or a wireless connection of some kind in place between those 2 points. And the other thing we need is routing information on the participating layer 3 devices. Okay, so when we think of layer 3 devices, of course, you automatically think of routers as being a layer 3 device, which is correct because they are. But what we often don't realize is that a computer is also a layer 3 device. Okay, it also processes traffic at layer 3. So it also needs the proper routing information for routing to work. So let's have a look at this scenario here. If user A needs to communicate with a device within the data center over here on 10.2.2.0/24, what routing information do the layer 3 devices within the communications path require? Okay, so let's have a look at the layer 3 devices. So, well, quite obviously, we've got this router right in the middle there. So what does that router, what information does that router need? Exactly, so it needs to have an address in its routing and forwarding tables. Okay, so it needs to have an address. What else needs to have some routing information on here? What about the actual user's device? Does it need any routing information? Huh? Yes. What does it need? Well, Okay, so I open, let's say I'm accessing a web server in the data center. I open my browser, point to the web server in the data center there, somewhere on 10.2.2.0/24. What does user A need what does user A computer need to get there? The default gateway. Yeah, you need a default gateway. So that is a pretty important point. You need a default gateway. Okay, so default gateway on user A, and we need to know, we need the network to be in the routing table of the router, which is pretty straightforward so far. So far, so good. Okay, so let's take a look at the concept of the routing table. So, the routing table is information learned from routing protocols and other routing information sources, like static routes, for example, would be another source. What's another source of routing information? Anybody got any ideas? Another source of routing information besides routing protocols? Static routes and we've got static. What's this word you think is hiding behind static here? It starts with DIR. What might that be? Directly connected networks. Yeah, that's our directly connected networks. So we're getting the routing table is populated by information from directly connected interfaces, static routes, and routing protocols. All that goes into the routing table. The routing table then feeds that information into the forwarding table. Okay, so what the routing table will then do is it will select an active route to each destination. And with that active route, it will then populate the forwarding table with the active route. So the main unicast routing tables are called inet.0 for IPv4 and inet6.0 for IPv6. So they are the two main default routing tables that exist. We can create others, and we will create others as we go. All right, so we've got these two routing tables, one for IPv4, one for IPv6. Let's look at this concept of how routing sources are evaluated. All right, we looked at this concept in Cisco as well. It's a concept which is called route preference. So route preference is about ranking the source of the routing information. So primary criterion for selecting the active route, it's one of the primary criterions for selecting the active route, used as a tiebreaker when the same destination prefix is available through multiple sources. So here is the route preference. We have direct routes have a default preference of 0, local routes 0, and static routes 5. So we go on, OSPF internal routes 100, RIP, sorry, OSPF internal routes 10, did we read that right, did I? 10, RIP is 100, external routes 150, and then we've got BGP, both eBGP and iBGP are 170. All right, so what is the point of that? Anyone tell me? What is the point of that? The first thing to notice is that the lowest number is the more preferred. Now, was there an equivalent to this concept in Cisco somewhere? What was that called? Anybody tell me? What was this? What was it? Administrative distance, exactly right. So administrative distance in Cisco, it is exactly the same concept as route preference in Juniper. It does exactly the same thing. The actual numbers are different in Juniper. But it, it does the same thing. Okay, so excuse me. Here we have two routes to the same same network, 10.1.1.0/24. We have got a static route there. The next hop on the static route is 172.29.30.253. It's going via interface GE0010. We also have an OSPF route to that same network, and it's going via interface 0013. Okay, so if you'll notice these two routes, the static one's got a little asterisk next to it up here. The asterisk means that is the active route. You'll also see that the static's got a /5 and the OSPF has got a /10. They are the route preference. Okay, so we've got two routes to the same network, but only one of them is going to be the active route, and therefore only one of them is going to arrive in the forwarding table. So it's only the active route that arrives in the forwarding table. Okay, so we can do a show route and see all the routes that are there, but we can also see which routes are active as well. If you look down the list, we've also got a direct route there with a preference of 0, a local route with a preference of 0. In fact, the local and the direct are derivatives of the same thing, the fact that there is an interface connected to a particular network. You notice that the direct shows you the subnet mask, well, actually the site notation subnet mask of the network, and the local shows you the IP address that is configured on the interface itself. Okay, so as we saw, that's the asterisk that signifies that a particular route is the active route. So far, so good. Okay. Now, so we've got the forwarding table. Restores required information for packet forwarding operation. The contents include the destination prefixes and the associated outgoing interface. So we can view the forwarding table by looking at the command or entering the command show route forwarding table, and that'll actually show us what's in the forwarding table. It displays in a slightly different format, but you'll still see the routes there. Okay, determining the next hop. The device compares incoming packets against the forwarding table entries to determine the appropriate next hop. If multiple matches exist, so in other words, if there are multiple routes in there that match the packet, which is quite possible and probably is going to happen fairly often, then it uses the most specific entry. That is known as the longest match principle. Okay, the most specific entry. To forward the packet to the destination, if there is no match, then it sends a destination unreachable notification back to the source, and of course drops the packet. Okay, so if there is no match, the packet is dropped. That's how all routers work, not just Juniper routers. All routers do that. Okay, so let's take a look at this scenario here. This is our forwarding table. So looking in our forwarding table, what we're seeing is that we've got, first of all, we've got this default route here, and we've got 3 other routes that are sitting underneath, all starting with 172.19. All of the routes, let's have a look here. So those last 3 routes are all going out different interfaces. So let's have a look at the next hop interface for packets destined to 172.19.52.101. So when that packet arrives at the router, and we do a lookup on a forwarding table, which interface will that packet be sent out of? 172.19.52.101. What's the answer, guys? Which interface will that go out? Will it go? So really, we've got three choices, all starting with 172.19. So it's one of those three. Right, it's one of those three. We've got two of them starting with 172.19.52. So in reality, it's one of those two. Which one? Is it the top one, or is it the last route or the second last route? We've got a 50-50 chance here. Okay, so basically, the /28 gives us a block size. Okay, what is the block size of the /28? Begins at 16, ends at, where's the next block begin? How about that? What? How big is the /28? What is the block size of that? /28 is a block size of, hello, 16, okay. So basically, it starts at 16, the next block will start at 32, okay. So, is that number in between 16 and 32? No, it isn't. So, therefore, it will go out interface GE001, okay, the second last entry will be the forwarding entry, because it does fall within /24, doesn't it? Yeah, it falls within there, okay, but it doesn't fall within here. The next one, okay, 172.19.52.21, what about that one? That does fall within this block, doesn't it? Yes, it does. It falls in that block. So it's going to go out interface 002. Okay, this is called the longest match principle, or the most specific route. Okay, yeah, just go and get interface 02. What about 172.25.100.27? Where's that going? Anyone? Pardon? Is it going to be dropped?
Do we have that full row? Do we have that full row? If we don't have, it's going to be dropped.
What about this one up here? Our default.
Default, yeah.
So yeah, it'll go out 000. Okay, because it matches everything matches the default. Okay, so it'll go out there. So so what we're looking at here is the concept of matching the most specific route, okay, known as longest match. That's how routers work. That's how all routers work. Okay, that's how routing works. All right. So here we are let's look at a concept of routing instances. So we have a default routing instance, but we can create others. So this is our master routing instance. This is the inet.0 IPv4 routing instance. That will be there in your router by default. That is there. You don't have to configure anything for that to be there. It is possible, however, to create extra routing instances. Okay, now what we do with the routing instance is we create them, we add interfaces into the routing instances, and we can add protocols in there as well, like for example OSPF, static routes, etc. Okay, right, so with these routing instances, it's a unique collection of routing tables, interfaces, and routing protocols. So we've got two there. We've got routing instance customer A and routing instance customer B. Now, I want you to bear in mind, you're thinking, well, what's this all about? I want you to bear in mind that a very, very large part of Juniper's market is internet service providers or carriers. Okay, so we're kind of used to thinking in terms of an enterprise or a business, but we need to start also thinking in terms of a carrier. All right, now carriers can have multiple customers which may have different routing requirements. So you may be providing specific routing services to a customer, and you may need to create a routing instance so that their traffic gets routed differently to other traffic. Okay, so you may create a routing instance for that purpose. Okay, so we have a default routing instance, which is the master instance, the primary instance for all devices running on Juniper operating system. It is inet.0, which is the IPv4 master routing instance. If we were to run the command show routing instances, that's what we would see. We'd see inet.0, inet6.0 for IPv6. We can define routing instances. Now, so a routing instance, we're kind of used to the concept of traffic coming into a router, going into a routing table, doing a lookup, and then getting routed out of an interface. Okay. However, it is possible, to have a whole separate routing table for traffic. I might say, well, if traffic comes in on this interface, then I want to route that traffic differently to traffic that comes in on another interface. Is that possible? Yes, it's possible. How do I do that? I do that by setting up routing instances and saying, these interfaces belong to this routing instance, these other interfaces belong to another routing instance. Therefore, if traffic arrives on this interface, which is connected to this customer, I'm going to route it in this particular way, but if it arrives on another interface, it may be associated with another customer or some other particular purpose, I'm going to route it differently. So, this is a new thing. We didn't do this in Cisco, okay? But it is a relatively common thing, particularly in service provider routing. Okay, so we can create this routing instance. You will do this, by the way. You will create routing instances. They're a very commonly used thing, particularly in service provider environments. So you'll go in and you'll go to edit routing instances. You will create a routing instance. The command is set instance type. There's various different types of routing instances we can create. We can create a forwarding instance. We can create layer 2 VPNs. We can create an actual virtual routing instance, VPLS routing instance. So there's a number of different things we can do. Virtual routing, forwarding instances. So they all have different purposes, and as we go through our networking journey here with Juniper, we will get to use quite a lot of these along the way. Okay, so here's an example here. We are creating a routing instance. We've called it new instance. When we do a show, we will see the instance type, which is virtual router. We put some interfaces in there. We've set up a static route. So here we have a static route, a default static route, in fact, with a next hopper 172.26.25.1. We've also added some protocols into it, which is OSPF, and we put some interfaces in there as well. Okay, so we've kind of gone into our routing instance and set up some routing information. if I do a show route table and then reference the instance, we'll see the routes, the routing table for that routing instance. Okay, so this is not the default instance, this is the routing table for that particular routing instance. And the software automatically will create the IP unicast table when you configure the corresponding routing instance. So there's our routing table for our routing instance. Now, let's have a look at working with routing instances here. So referencing the routing instance name when viewing information for a given instance or sourcing traffic. So for example, if I was going to do a show interfaces terse command, but I wanted to see the interfaces that were in a particular routing instance, I'd go show interfaces terse, routing instance, and then name the instance. So in this case, we called it new instance. That was the name of it. And then I'd see those interfaces. The other thing is, if I wanted to test connectivity with those interfaces. So in other words, if I was saying, well, I want to make sure that I can connect to my next hop router, for example, from these particular interfaces, and I'm going to do a ping. What I'd have to do is in the ping, I'd have to reference the routing instance and put the name of the routing instance. So the Rapid 25 thing here is completely optional, by the way. Normal pings work just as well. So I could go ping 172.26.25.1, routing instance, new instance. And that would then tell me whether I had connectivity or not. This rapid count 25 is just an option that you get to put onto the ping command. Whether or not you're using a routing instance with it is irrelevant. It just works either way. Just shoots 25 packets out. Okay, same goes for trace route. If I'm looking for connectivity from an interface that's in a custom routing instance, I have to put the routing instance on the command and tell it the name, or specify the name of the routing instance for the trace route to work. Okay, so what we've actually got here is multiple routing tables, and I need to make sure that I reference in a ping or a trace route command the particular routing instance that I need to use to achieve that particular connectivity that I'm looking for. Okay, so that's just something to, it's kind of a different thing in that inside one router, we've got multiple, we can have multiple routing tables, all routing slightly differently depending on which interface the traffic is coming in on. Okay. All right, static routing. This is something we're relatively familiar with. Manually configured routes added to the route table. So, find under Edit Routing Options requires a valid next hop. And typically the IP address of it, which is, the next hop is typically the IP address of a directly connected device, so that, for example, if we're down here on network A, my next hop is going to be the 172.30.25.1/30 in that particular case. So if I was saying, show me a route to 192.168.63.14, which is our endpoint up the end there, what I'm going to see is that I've got this default route, and that default route has a next hop of 172.30.25.1, which is in fact, in this case, that would be the gateway of my internet service provider. So really it's the other end, was my internet service provider's gateway. So it's kind of what my interface is connected to. So this is an example of configuring a static route. So we're under Edit Routing Options. We're just doing a show. This is an IPv6 route here. and this is the default IPv6 route. Next hop, which is an IPv6 address, and then we've got a default IPv4 route down there as well with its next hop. I might just draw attention to this no re-advertise parameter there. That is, you'd kind of use that parameter if you were setting up a route to your management network. Okay, so just say, for example, I'm configuring up my router and I am managing my network from somewhere else. Okay, so I need to put a route. I'm going to put a route in my device so that when I log into my device knows, my router knows how to get traffic back to a management network so I can communicate with it. This no re-advertise is a really good statement to put in those types of routes, because what it means is that if I import that route into another protocol, that this particular route will never be imported into another protocol because it's designated as to never to be re-advertised. So in other words, it's a static route. Let's just say I wanted to take all my static routes and make OSPF advertise all my static routes, which I might be a good reason for that. Then this route would never be included in that. It would never re-advertise that particular route. Okay. What about monitoring? Monitoring static routing. Here is the command, show route protocol static, and it will pull up our static routes. We can take a look at that. We use ping to verify end-to-end reachability as usual. Okay. Next hop resolution. So by default, the software can only resolve directly connected next hops. If you're going to put in a next hop that is not directly connected, so in other words, normally I'm configuring router A. I want to put a route to the 172.20.3 network, which is down the end there, sort of past router C. So I want to put a route to that network there. We'll put it as a static route. Generally speaking, my next hop is going to be 172.25.1.2, all right, which is the IP address of the next router down the link, okay, the router that I'm directly connected to. If I'm not going to use that as the next hop, but I'm going to use the next router down, router C, as my next hop, you then need to include the resolve command under that. Okay. Now let's look at the concept of a qualified next hop. The qualified next hop allows me to set a different preference on a particular static route. So by default, the route preference for static is 5 by default, okay? And when it comes to route preferences, the lower the number, the better. The lower the number, the more preferred that route is. What if I have got two possible next hops on a default route? How could I have two possible next hops on a default route? Well, what if I've got two internet connections? Okay, I've got a nice fiber connection that comes into my premises, and in normal operation, I'm going to be sending all my internet traffic out through my fiber link, okay, because that's my best connection. But what about just in case I lose my connection, just in case I know the ISP has a power failure, none of their generators come on, everything just shuts down, boom, no internet for whatever reason. I have also got a 4G connection, and I want to use my 4G connection as a backup plan, okay, just in case I lose my fiber. So I've got another ISP, or maybe the same or whatever, probably another ISP that's providing that connectivity through that 4G connection. So what I would do is I'd set up my default route. I'd give my next hop address to the ISP that's providing me with my fibre connection, but then I could go and put in a qualified next hop, which then has the next hop of my 4G connection. But I give it, so by putting in qualified next hop, it gives me the opportunity to putting in a different route preference. So I give it a preference of 7. So what does that mean? What would be the effect of a default preference on my first next hop, but a preference of 7 on my second next hop? What would be the effect of doing that as far as the routing table goes? What would that do? What's that? Okay, so the lower the number, the more preferred. Yeah, okay. So what effect would that have? What would that do? As far as my routing table goes, I've got 2 next hops now for the same route. So I've got a default route with 2 next hops.
It will take the 5.
It will take 5. So the active route in my routing table will have a next hop of 172.30.25.1. Okay, until I lose connectivity to that next hop, and then the second one will go live straight away. And when the first one comes back again, then it will go live again. Okay, so it's a way of setting up a backup, kind of a backup next hop. All right, so we've looked at static routing, we looked at route preference, looked at qualified next hops, of where you get to set a different route preference. Let's take a look at dynamic routing. So a method of dynamically learning routing information, as we know. The following benefits are lower administration overhead, increased network availability because the routing protocol can dynamically reconfigure itself, and also greater network scalability because we get to grow our network without having to configure static routes everywhere. Okay, so dynamic routing protocols, let's have a look at an overview of them. We have got 2 basic categories, IGPs and EGPs. IGPs, what are the characteristics of an IGP? They operate within a single autonomous system. Remember that word again, autonomous system. Okay, so what does that mean? Single network administration that provides unique routing policy and flexible use of network resources. Examples include RIP, ISIS, and OSPF. Okay, they are examples of commonly used IGPs. Pardon? Yeah, so these are for routing within an autonomous system. Okay. So, then we've got EGPs. Well, there's only one. Independent administrative entities that communicate between independent network infrastructures. Current EGP used today is BGP. So the thing about an IGP is that when you set up an IGP, you're communicating between routers which you kind of own. I mean, they're part of your network. All right, so in other words, the traffic that's going between them is totally controlled, and you want communication between those routers. You want traffic to flow around in your network. So that's the purpose of your IGP. It's your network. So you're quite happy for the IGP to set up connectivity between all your routers and make everything just work. You're quite happy for the IGP to kind of do its thing, okay, automatically, create the connectivity that you want. When it comes to BGP, what you're doing is you're setting up connectivity between your network and somebody else's network. All right, now you don't want that just to happen automatically. You want to totally control that process, all right? So BGP is a totally controlled protocol. There's a lot more controls in BGP than what there are in an IGP protocol. So, and also, when you're setting up BGP, there are generally some kind of commercial arrangements that go around that as well, in that I'm paying somebody for the privilege of sending my traffic up through their network, or I'm charging somebody for the privilege of them sending traffic up through my network, or whatever it is. Okay, that's kind of commonly how it works as well. So here we have independent autonomous systems, and we have got eBGP, and between the systems, and we're running iBGP within the systems as well. All right, so eBGP between, and iBGP is running inside the systems. Okay, so we'll do quite a lot of work on BGP in this course. Get to set that up. Okay, looking at OSPF, what we know about OSPF is that it is a link state protocol. What is a major difference between a link state protocol and, say, a non-link state protocol like a distance vector protocol, or even BGP, which is really known as a path vector protocol? What would you say a major difference is between those two? As to how they operate. The difference between OSPF and BGP and RISC? Well, no. The difference between a link state protocol and a non-link state protocol. Okay, so BGP is not a link state protocol. All right. Let's just say RIP is not a link state protocol. Yeah. So what is the difference between those two? They update the information. The routing information. Because the vector designers, they have a period of time that they are sharing information. The one is when something is going to fail, you are not going to. I would say that probably the key difference is that non-link state protocols learn routes from other routers. So another router will advertise its route saying, hey, I've got routes to all these networks, and it will advertise its routes to other routers. So a router will receive a route advertisement from multiple routers. It will then evaluate the route advertisements that it's received and work and say, well, actually this one is more preferred than that one, based on metrics that are associated with those route advertisements, and it will select the best route from the route advertisements that it receives. So with non-link state protocols, routes are advertised to other routers, route advertisements are received by a router and evaluated. Okay? With link state protocols, no routes are advertised to other routers. What happens is the state of each individual link or interface is advertised to other routers. So it will say, well, I've got this interface connected to that network, this one's connected to that network, this connected to that network. The state of my interfaces are up, so all my links are up, and that is advertised out to all the other routers. So that information is collected by each router, and then what happens is the router then calculates the best paths to each network. So the router builds a picture of the entire topology and then calculates the best path to every part of that topology. Okay, so routes are not advertised and evaluated. Link states are advertised. A topology is built and routes are calculated. So basically the router figures out for itself the best path to get to every single part of that network. Okay, so they're calculated routes. Okay, so link state IGP floods link state information to its neighbours, creates a complete database of the network, and then calculates the best path to each destination network. We also use this concept of areas to allow for scalability, primarily efficiency and scalability is what the concept of areas provide to us. Okay, so we're looking at a link state IGP, a single OSPF area. We're going to use a single OSPF area to provide connectivity among all connected subnets and loopback interfaces. We're going to ensure that no adjacencies are formed. So this is our little goal here, our little project that we're going to do. We're going to ensure that no adjacencies are formed on interfaces connecting to the 172.20.x.0 subnets. So we've got 3 routers here in OSPF area 0. So in this little scenario, we don't want any adjacencies connecting to 172.20.x, so 172.20.1.3 down there, and .2 over there. We don't want any adjacencies forming with anything out there. But we do want connectivity amongst all of these routers, including their loopback interfaces. Let's take a look at how we achieve that. So here we are in Edit Protocols, OSPF, we're on router A. We're going to set area 0 and we're going to set that on interface, and we're going to include interface GE001. .0. Okay. And we're going to do the same for interface 002, the same for interface 003, and for the loopback interface as well. Except when we do 003, we're going to include the passive command on that. And we're going to include our loopback interface in our OSPF protocol, which is actually a good practice to do that. You want to generally include your loopback in your OSPF protocol. If we take a look at that, we can see that all our interfaces are included and GE003 is passive. And we use the OSPF neighbor command to display the state. So there we are. We've got our state being full, which means we have formed adjacencies, essentially. And we can then view the routes, so we can go show route protocol OSPF, and we'll see all the OSPF routes in our routing table. Okay, so in this chapter we had a look at basic routing operations and concepts. We viewed and described routing and forwarding tables, configured and monitored static routing, and configured and monitored OSPF. All right, so I want you to notice that it was under the Edit Routing Protocols OSPF hierarchy, and we simply included all the interfaces, referenced all the interfaces that we wanted to include in the protocol under that hierarchy. All right, so let's have a look at some review questions. What are the 2 key requirements for routing traffic between 2 remote devices? So we said there was 2 things. 2 key requirements, what were they? Well, the first one was we needed an actual connection, right? A piece of cable or a wireless connection of some kind. That was the first thing. And the second thing that we need is we need routing information in the layer 3 devices along the way. Okay, so we need information. That's a very important point. If you don't have information, you can't route. If you don't have information about the destination network, then no traffic will be sent there. It will just be dropped. All right, so that's why if you control your routing protocols, you will control your traffic. Okay, so setting up the routing protocols correctly will mean that your traffic will flow correctly. All right, list the default IPv4 and IPv6 unicast routing tables. What is the name of the default IPv4 unicast routing table on a Juniper system? Exactly, inet.0, and the other one is inet6.0. Which primary criterion determines active routes within a routing table? So we're talking about the selection criteria that has to do with the source of the routing information. What was that again? What do we call that? What's the name for that? Huh? It's called route preference. Route preference. Okay. And which configuration option allows unique preference values for a static route to the same destination? So that means I've got two next hops for the same route. What was the particular configuration option that allows me to put a different preference on one of those? Qualified next hop, exactly. Yep. And list some advantages in using a dynamic routing protocol instead of static. Oh, less work. Okay, that would be the #1 advantage. And also, the network can dynamically configure itself if there's changes to the topology as well. Okay, we are going to take a short break right there.